Shall we start now? There are 26 participants.
Maybe we need we wait for another 2 minutes?
Okay. I think we can start now.
Yeah.
So
Yes.
okay, we'll start. I welcome you all to this session. This is the 10th session of our program. Our resource person is with us. Now, I welcome him to start this session.
Thank you, ma'am, once again. So we have covered some basics in Python as well as um, some advanced topics like handling symbolic variables, and in addition, how to play with basic calculus techniques and plot simultaneously something related to basic calculus, handling discontinuities. These things we have seen. These are some trickier questions that we usually face. So today we are going to see something coming out of the numerical analysis, because numerical analysis is usually used when pure mathematics fails to actually answer certain things. For example, we know most of us who have undergone already a course in Galois theory, the field theory, they know that solving a fifth degree polynomial, there is no general formula for finding out the root of a fifth degree polynomial. Okay, that's actually an outcome of the Galois theory, or if you want to say, a motivation for the Galois theory to actually begin. So, in such situations, mathematics is not just used in pure mathematics, where finding solution is actually considered to be something called a pressure. Mathematics is used in many areas where it's actually finding solution is actually a requirement, not just a pressure. So, especially in applied fields. In such situations, finding the exact solution of a problem is not always necessary. So, getting something very close to, so very close is actually, it depends on person to person, need to need. So, finding an answer very close to the actual answer is more than enough in most of the practical applications. Numerical analysis comes into the picture in this particular scenario, that whenever you want to find a solution, it's not necessarily going to be exact, even if you are getting something very close to the actual answer, with the error being something within a predefined range. So that's more than enough for most of the applications. Numerical analysis is precisely used for that. Numerical analysis actually consists of methods for finding approximate solutions in many of the problems, and developing an analysis in the sense that after finding solution or after finding the technique to find out approximate solution, we need to actually analyze whether that solution is going to be very close to our actual answer, and how do we make sure, how do we theoretically argue that this particular technique is going to give the actual an answer very close to the actual result. Okay, numerical analysis is that branch of mathematics which deals with approximation as well as estimating the effectiveness of approximation. So we are going to see a few methods in numerical analysis for interpolating polynomials. Some famous methods are there. So we will see how to implement these methods using Python modules like numerical Python, symbolic Python, etc. That's what we are trying to do today. I don't know how far we will be able to cover. So let us see that the problems that we can do today. Okay, let me start sharing my screen. Before that, let me start a Google document. Starting a new document. The code is here. Okay, this is where I'm going to paste the code that I am going to prepare. So let me start sharing my screen. Okay, so finding the very first thing, the interpolation technique is actually used for finding out a function, finding out not exactly a function we cannot actually find out. Suppose that some values of the function is given. Most of the times, what happens is that function itself may not be known to us. Okay, so we will be finding out some data using some experiment, using some computation, and we will be having x coordinates as well as corresponding y coordinates. Y coordinates are measured using some technique, not exactly using a function. We don't know the function, because if you know the function, there is no need of interpolation. So in such a situation, we have certain x values, we have certain y values, and we may want to compute the y value corresponding to some other x value. Okay, so we already have a set of x values. We have corresponding y values. Now we may want to compute a y value corresponding to an x value, the x and y of which are not given in this particular set of values available with us. Okay, this is what exactly we want. This is known as interpolation, and the interpolation also happens to be in mostly in two ways. The x value in between the x points already given to us, and the x value outside the x point given to us. So it can happen in two ways. And one more thing is interpolation as well as curve fitting. There are two things. So interpolation essentially means that we are trying to find a polynomial function that approximates the actual function, in the sense that the polynomial passes through the given x5 points. So you may be having x1, x2, etc. to x10. Correspondingly, you may be having y1, y2, etc. to y10. Interpolation, what do is interpolation finds out a polynomial that passes through x1, y1, x2, y2, x3, y3, etc. to x10, y10. Once we have found this polynomial, once we have approximately found or guessed this polynomial, then an x11 value Given an excellent value, you have already computed a polynomial which passes through these data points. Then you will be able to find f of x11, which is binary. Okay, that's what interpolation is. Now, curve fitting is slightly different. Curve fitting is usually used when we definitely know that there is some error in actual data. So we are trying to construct a smooth curve that more or less passes very close to these data points. Okay, it's not entirely a curve passes exactly through this data points, but that may be in some sense. Sometimes that may be much better than the interpolating polynomial. Okay, so that's the basic difference between interpolation and curve fitting. These are essentially used for one is used for finding out a polynomial and the other is used for finding out a smooth curve, which not necessarily passes through all the data points, but it's very close to all the data points. And sometimes curve fitting is going to be a much better approximation than the polynomial that we have constructed for finding out the value of f at x11, assuming that x1 to x10 values and y1 to y2 values are given to us. So there are, and many of you might have already gone through a course in numerical analysis, and maybe you are all familiar with these type of analysis. So initially, what we are going to do is that we are going to try with the polynomial interpolation using Lagrange's method. Now, one more thing is that given x1, y1, x2, y2, x3, y3, etc. Definitely, quickly we can actually find out a polynomial that passes through all these points. It's very easy because suppose that we are taking x minus x minus y1, x minus x1 into x minus x2 into x minus x3 into etc. Sorry, x minus y1 into x minus y2 into x minus y3 etc. Then if you are substituting instead of x1, that x1 it passes through x1. All these things are possible. Now, Lagrange polynomial is actually slightly better version of all these things. So in Lagrange polynomial, what happens is essentially is that suppose that the points given are x naught up to xn. Okay, let me just write down these assumptions first so that we can easily go into the programming part. Let me just type a little bit of a theory about that. Suppose I'm just typing points x naught to xn given. So n plus 1 points are actually given here. Okay, x naught to x1, n plus 1 points are actually given here. And suppose that correspondingly y1, y2, etc. up to yn is given. Y0 to yn is given. Suppose that these many things are given to us. Now, Lagrange's formula actually gives you something called a Pn of x, which is a Lagrange polynomial. Lagrange polynomial is given by the equation. So Lagrange polynomial, let me just call it as L of x, or maybe even Pn of x, P underscore n of x equal to. So Lagrange polynomial is now it's a summation. Sum from I0 to n. I'm just writing it like that, not in LaTeX mod. Simply, I'm straight away writing sum from I equal to 0 to n. Now we have yi into another polynomial li of x, where li of x, the computation part comes here. I'm not going to the details of the theory behind deriving all these things. I'm just going to compute that. That's it. Li of x is given by. So Li of x is given to be it's another kind of polynomial, and Li of x is given to be the polynomial equal to it's a product which is equal to product j equal to 0 to n x minus xj by xi minus xj. So it's a product of the form product j from 0 to n. I'm just typing it so that we can easily convert this into Python code, where j not equal to I, and the product of what? A product of all the not rational functions. It's again polynomials, x minus x naught. So x minus x naught divided by xi minus x naught, xi minus x naught. This is the product. See that j is also here, so we should take care of j also. Now, Okay, on the other hand, I have already taken x minus xi by xi minus xj. That's enough. X minus xi by xi minus xj. So this is what the end of x is. I equal to, so where I from once again 0 to n. So this is for the Lagrange polynomials. So what do you call it, aim of this session is actually to find out this polynomial. We would like to see how to evaluate this polynomial, and not only that, we would like to see that how accurate this particular polynomial is. For that, what we are going to do is that we will initially consider a function. For example, we can take sin x itself. We will initially consider a function. We will create some. We will take some x points. Correspondingly, we will find sine of x. Those points will be the y points. And corresponding to this particular function, forget about this sine of x, so that we want to just see that how the approximation is, how nice or how better, how good the approximation is going to be. Therefore, we will forget about sine x. We will create a polynomial function using this method. After that, we will try to see using the graph. We will try to see that whether the sine function and this particular polynomial approximation, they are passing through the same points, and how far they are different, how far they are at how many points, or not at how many points, how much they are differing after on looking at the curves. That's what we are trying to do. Okay, so let us start. These comments are here already, so let me just comment out if this is clear. Okay, so what are the points given to us? Initially, we need to create a few points. Okay, so to understand whether we are doing it correctly or not, let us take a familiar function, not a polynomial function, because polynomial function is very easy. So let us take a function which is not a polynomial function. For example, the familiar function is sine of x for us. So from numerical function, import numpy as n. So let us create x points. X is equal to, so x points, suppose that we take in the range 0 to 2 pi, so that it will be on the positive side all the times. Not necessarily. Np dot linear space we can take. Linear space 0 to 2 star np dot pi. And suppose that we take okay, let us take 100 points. After that, we will try to vary the number of points and see, okay, 10 points is enough for the time being. After that, we can try to increase the number of points. The polynomial also will be increasing the degree. Remember that each polynomial lix, each polynomial lix is having x minus xi by xi minus xj. Okay, where this x minus xi by xi minus xj, this xj is varying, and we are taking the product over j. Okay, remember that. So, and it's a sum. Pn of x is actually the sum of LAX. So, what is the degree of Pn of x then? Pn of x degree is going to be equal to, see, each LAX is j from 0 to n. So, corresponding to x minus xi, so j is from 0 to n, but so corresponding to each j, we have x minus xi. Okay, corresponding to each j, we have x minus xi. But j is not equal to I. So one ij is missing. Therefore, there are n minus 1 x minus xi's. Sorry, 0 is also included. Therefore, there are n x minus xi's. So n x minus xi means that LAX is a polynomial of degree n. So Pnx is the sum of all these LAXs. Therefore, Pnx is also a polynomial of degree n. Okay, so if you are given 10 data points, if you are given data points from 0 to 10, not 10 data points, if you are given data points from 0 to 10, then our polynomial will be of degree 10. Okay, the polynomial we construct will be of degree 10. So if you are given 100 points, the polynomial will be of degree 100. In that case, the approximation also will be better. We can see that. Okay, now y points equal to np dot oh no, sorry, just sine. Np dot sine of x points. Let us see, we have taken only 10 points. Let us see the output of this x points. So x points, there is no need to take because we have taken the points from 0 to, so y points only we need to check. Let me save this first. Ask, what's the program? 49. I'm saving this under the name Lagrange interpolation, trying to see the output of this. by as NP, unexpected intent. Okay, sorry. Oh, everywhere. X, Y, YTPS, sorry, YPTS. So these are the 5 points we have. Okay, it's not much useful anyway because we don't know what exactly whether they are going to. Okay, if you want to see plotting, we can try the plotting. Import by plot as PLT. This is standard command that we always use. So whenever we are trying to do some approximation problem, whenever we are trying to see whether something is correct or not, it's always better to plot the graph and see. Okay, it's always better to plot the graph and see so that we can get an idea about if our calculations are going in the right direction or not. So importing matplotlib is imported. Now trying to plot PLT plot x points, y points. The plot is here. So you can see that because the number of points we have taken is much less, it not does not really look like a smooth curve. Okay, if you want to increase the number of points, then it looks like somewhat better. Okay, this is the plot we have. Now we are going to construct this this what do you call for constructing PLX. We know that we need to construct LIX. So how do we construct LIX? That's the first question. So we need to create all the LIX polynomials. Okay. So LIX polynomial also inside after finding all the LIX polynomials, we need to find the sum of all LIX polynomials. That's what the technique is. Remember that this Li of xj, what is Li of xj? Li of xj is going to be equal to, if I is not equal to j, Li of xj is going to be equal to 0. If I is equal to j, Li of xj is going to be equal to 1. So we can call it to be equal to delta ij. Okay, so the error also we can try to estimate after that. Now, how do we find Li of xj? What is technique for finding Li of xj? Remember that we need to find out so many polynomials. So how do we do all these things? What is the way to do all these things? Okay, let me copy and paste up to here in the Google document so that if you want, you can try. The code up to here is copied, pasted. So remember that we have so many polynomials to be plotted. So the L1 polynomial is there, L2 polynomial is there, etc. up to L10 polynomial is there. So what is the way to do that? So maybe we can create an array. So I don't exactly have a method in my mind. I'm just trying. So if you have any better suggestions, we can give that. So L polynomials. I'm calling it to be L polynomial. I want to push this L polynomial. I want to calculate each and every L polynomial. Maybe the list comprehension also should work there, but I'm not very sure about that. I'm just trying. After that, we can try to improve this function. Okay. After this, after finding this technique, you may be already, since you are already have already gone through a few lectures, you might have already seen this problem. You may be having a better method than me. I'm just trying. So L polynomial, for from where to where I need to create this polynomial, I need to create the polynomial from j equal to 0 to n. So for j in range, so 0 to the number of points, let us just take n PTS equal to number of points, length of x points, so that if you are changing this 10 to something else, we don't have to worry about that what it is. We can simply use number of points, or even n itself is. So length n is actually 0 to n. Therefore, suppose let us take it to be equal to length of this minus 1. No, we are anyway taking, this is better, range n. So what are the polynomials that we are going to create? Range n plus 1 do we require? J0 to Jn is required. So maybe uh, n plus 1. So what is the first polynomial that we have to create? What are the things that we have to multiply? So we have to multiply x minus xi. This is the definition. X minus xi by xi minus xj. This is what we want to do. So x minus xi by xi minus xj. J is now fixed. So we need one more. X minus xi is also required for I in range. So this I is also varying from 0 to n plus 1. So there are multiple loops. Two loops are there. So what is it now? L. Suppose that we call this to be Li equal to, what should we multiply? Initially, let us define Li to be just equal to 1 so that we can multiply each and every polynomial component in this. But remember that now there is a small problem that we can see that here we are going to multiply something x. X is actually a symbol. Remember that x is a symbol. So if you want to create a symbol, you definitely need to import symbol. Use symbol from symbol import symbol called x to be a, and after that we can try to evaluate it using substitution. Symbol x. Okay. So what next? So we have here this. So what is it that we have to multiply? X minus xi by xi minus xj we need to multiply, provided that j is not equal to n. Okay, so okay, LIX we are creating. LIX. What is what exactly we are creating? We are creating LIFX. So if you are creating LIFX, the I should have been actually on the top, not here. I we should take here. J we should take here. J in into 1. What is next we have to do? We have to multiply with Li. What should we multiply? And provided that J is not equal to n. If J equal to I, so what should we do? If j is equal to I, we do not do anything. We need to go to the next I. Sorry, next j. So we will continue. The meaning of this statement, we have not used this continue so far. The meaning of this statement is that suppose that I is 1 and j is, suppose that I is 0 and j is also 0. So the 0 value of j will not be taken, j will be incremented to 1. So j1, j2, j3, etc. will be taken. So continue means that go back to, take the next value of j. Okay, that's what the meaning of continue is. You don't go further downwards, but go upwards and come up with a new value of j. So what should we multiply? X minus. So x values are here. X minus x points, xi values we require divided by what is it? Xi or xi minus xc. Xi minus xc. So after completing that, what should we do? Let us push this to the L polynomial list after completion. Append Li. Okay, after once this loop is over, all the L polynomials will be created. Let us try to see if it's correct or not. Print L. So L poly means L poly 0, L poly 1, L poly 2, etc. So how many points we have taken? 10 points. Okay. You see. Let me suppress the program. So Let me just take only 2 points to see it better. So this is not required. Y points, suppressing it. So how many points are here? Polynomial of degree n. So we are going to construct a polynomial of degree 2. So this is first polynomial. This is second polynomial. Therefore, the product of these two L polynomials, there are two. No, no. Length, it is 0 to n. 0 to n means that it's going to be n. It's going to be n minus 1. Okay, that's not correct. So there are 2 points. 2 points essentially means that it's x0 and x1. Therefore, a degree 1. Sorry, this is correct. I guess that this is correct. Okay, let us see it in here. So these are the points. So once we have found out this polynomial, once we have found out this L polynomial, what is the next thing? Lagrange polynomial. Lagrange polynomial, what should we do? What we need to do is we need to take I from 0 to n, yi into Lx we need to sum. Okay, so we need to sum. So maybe we can take list comprehension. We just try sum of y value I. This is yi star li L poly I. So this is the product of that. Product is taken 4 I in range n should be printing. Lagrange polynomial is here. It's a degree 1 polynomial. Let us increase the degree to 0, to 10. Okay, we don't know whether exactly it is because the multiplication has not taken place. We can expand it, of course. Okay, trying to expand. I think it is expandable. On expanding, we are getting a 9-degree polynomial because 10 points are taken 0 to 9. So this is correct. The polynomial is just fine. So now let us see the plot. Or the plot, not even plot, we can actually compare the x values and sign values and we can determine. Okay, x value, this for these points should be correct. So let us just try to compare first. And how good the approximation is, what we can do is that we can take another what do you call it, point outside this x0, x1, etc. to xn, and we can apply sign on that, and we can apply the polynomial that we have constructed on that, and let us see if the values are matching or not. Okay, that's how we can measure the accuracy at some points, at certain given points. Trying to plot. So let us plot both. Already the plot is imported. Maybe I will move it here. So this is plotted. Plot show, where is the show appearing? There is no show given anywhere. Okay, anyway. So after that, what should we plot? X points are exactly the same, but instead of y points, what should we take? Instead of y points, we need to take the Lagrange polynomial evaluated at this polynomial. Okay, can we do it like that? This is symbolic thing. So we need y points mu. y points or Lagrangian equal to, let us use list comprehension. Let us evaluate Lagrange poly. What should we evaluate? XPTS. Sorry, this is not the method. Substitute. Substitute XPTS I for I, or otherwise directly also we can x value for x value in, no need to count the number in XPTS. Substitute, no, substitute is in bracket. So there are two plots. Maybe we can specify the color also. Red dot, and here blue dash, blue dash. Expand is used. Why is it saying it's not used? Okay, somehow it's maybe expand is not used as a function, but we used it as a method. Okay, let's see. PLT show. Oh, sorry, for X. What's the problem? Can't convert expression to float. Where is it converting expression to float? Where is the error? X points, Y points, LAG. So what is this Y points? Let's try to see that. Print Y points, suppressing the plot. Or substitute for X, XY. Say that. Is it coming out? I guess it's coming out. Now let us try to see. How many points we have taken? 10 points. Take it 100. Evaluation is taking too much of time. Okay. It has given the polynomial, but for plotting we are still waiting. Oh, why is taking so much of time? I don't understand. Let me just stop and maybe I will try with 20 points instead of 30. Why is this coming as a straight and blue is coming as a straight line? Why is it like that? So much of error. B double dash. Okay, let us take instead of sin x, let us just take a polynomial itself or mod x. Let us take mod x is not very NP, but that's not very what do you call x square. Let us take instead of that. Okay, we just take x square, xpts square. I guess that this should work. Still, which is in red. Red is given by the polynomial, and blue is given to be x points and y points. Why these x points and y points are coming like this? In P linear space 0 to pi, uh, am I using something? Okay, let me just see from the beginning itself. X points is NP linear space 0 to 2 pi, 2 pi. So NP pi, NP pi, NP pi should be X point is up to around 6, that's correct. So after that, Y points, just print Y points, printing Y points, polynomial of degree n. Let me clear everything, clear console and restarting. X points are here, so Y points. Okay, let me just once again take two instead of doing all these things so that easily we can find out whether we are doing it correctly or not. So print X points, print. I'm just removing all these things. I'm not removing. I'm going to place it somewhere here so that I can copy and paste back. So up to here only I'm printing. So printing Y points and print X points. Just to analyze what exactly is happening. X points are, Y points are here. Name XGPS. Sorry, X points are okay. What are the X points? Polynomial of degree n. X points are 0, 1.0, etc. Now let me just take a range instead with a distance of 0.1. 0, 0.1, 0.2, etc. up to 1.9. Y points are 0, 0.01. Okay, that's perfect. That's correct. Now let me copy and paste. Let me just try to see. x points and y points in plotting. This curve seems to be somewhat better, somewhat fine. Now, creating the polynomial once again, copying and pasting. Okay, there is something wrong with the computation seems. Well, let us try to see with the computation. I think it's because mainly because I think the interpolation is given in red. The interpolation is having some problem. That's why it's going up to minus 200, and this is appearing as a straight line basically because this is not a straight line. Since the graphing window is too large, the graphing window is too large in the sense that the range of x and y are taken to be too large. X is just okay, but the range of y is going from 0 to minus 200. Therefore, the top one is just appearing as a straight line. It is not actually a straight line. Okay, it's not actually a straight line, but to fit into this window, it's appearing to when it tries to fit into this window, it looks like a straight line. That's not exactly correct. So where we are missing something, let us try to see the code once again. For I in range 1 to n, what are the things that we are trying? So we need to construct the Lagrange functions. The functions we are, the individual functions we are constructing using the formula, a product j from 0 to n, x minus xi by xi minus xj. J from 0 to n, Lix is nothing but j from 0 to n. Okay, let us see if Lix is correct or not. Lix, where is Lix? This is what Li is. For I in range 0 to, okay, 0 to, so what are the points that we are creating? Oh, so this is actually a confusion. That's 0 to n. 0 to n is how much? Linear space again, 20 points. So we have altogether 20 points. Take 21 points. So how many points are there? Polynomial of degree n. Polynomial of degree 21. But we don't have polynomial of degree 21, right? We have polynomial of degree. Since we have taken 20 points, we'll get polynomial of degree 20 only. Okay, so that's fixed there. Now, from where to where we have to run? I in range, we need to run I from 0 to 0 to n. So we need L1, L0, L1, L2, etc. up to L20 is required. So if we require up to L20, we need to take n plus 1. I think there is not much difference. N plus 1. So we should get a polynomial of degree, Lagrange polynomial, expand. Let us see the expanded polynomial. I'm cutting this much, trying once again. What is the degree of this polynomial? Degree of this polynomial is 20. So x minus xi by xi minus xj. Okay, once that polynomial x minus xi by xi minus xj is found, if j is equal to 0 is not taken, j is equal to 0, that is skipped. J is equal to I is skipped. So the polynomial is found. Now the Lagrange polynomial, the y value into the y value into the polynomial is here. So y0 into L0, y1 into L1, y2 into L2, etc. Y, what is the last polynomial? It is y20, so n plus 1. So But here itself we are getting the degree to be equal to 20. But Lagrange polynomial is from okay, because one is being skipped. Okay, let us see what is the degree of this polynomial. X to the power 20. Now the degree of the polynomial is x to the power 20. 19, 18. Okay, that should be correct. So Lagrange polynomial substitute for x. So to find the corresponding y values, we need to evaluate this Lagrange polynomial. So how do we evaluate x minus xj? Oh, no, x minus xi only. Have I done x minus x? Have I taken x minus xj here? X minus. Sorry. That's a mistake. Xi minus. That's correct. That's correct. The first is xi and it's varying. Oh, that's a mistake. That's x minus xi. That's what. Okay, thank you. Thank you very much. So, where is that? X minus. Where should I do? Where is that? Where is that mistake? Lagrange polynomial x minus xj. Okay. Perfect. Thank you very much. Thank you for pointing out. So that's a mistake. Yeah, that's why it is becoming so complicated. So now we can say that the curve is now completely perfectly fitting within, at least in this particular part we are seeing. Now we can try to change with sine also. Yeah, sine is also getting approximated better. But if we change the number of points to, if you reduce the number of points to say 5, then the approximation is going to be the sine curve is going to be something like this, and therefore hence the approximation is also going to be something like that. So this is how, okay, here product j to n where x minus xj, here also I should change. So Lagrange interpolation actually gives you an approximation given 0 to n data points. It constructs a polynomial of degree n, and it passes through all the points. Okay, if you want to see the points through which these things are passing, then that's also quite possible. Sine values and these points we can probably put a dot also. Where should we do that? These are the sine points which we are computing, and sine points if you are computing, you can see that, yeah, sine points are anyway already given. So these are sine points. So if you mark this as, maybe you can plot the sine functions. Okay, sine function is not necessary because, okay, even if you want y sine can be sine of xpts. That should work because xpts is a numpy array, np. Black diamond. Okay, since we have already taken sine points, that is not going to make much sense. Already we have taken sine points, only we have taken to be equal to, so this is not going to make much sense. Okay, that's it. Let me update the Google Sheet with anything. So updated the entire Google Sheet with this call. Please try in your Colab interface. So in a similar way, we can try to do interpolation using Newton's method exactly in the same way. So the only thing is that we need to know how to see. There are two things. One is that we should know how to evaluate these things in our own. If you are able to understand, if you understand, if you know the technique in numerical analysis on how to find out a solution using this particular technique, then the only thing left is to create a Python program using the tools that we have already understood, right? So that's not very difficult, provided that you know how to code it. Okay, let us now see Newton's method also. So Newton method actually gives two methods. One is forward differences method, and the other is backward differences method. Okay, so there are two. So So in the case of forward differences or backward difference, the thing is that we need to compute the differences. So forward difference as well as backward difference we need to compute. So forward difference essentially mean that we are given that x naught, x1, x2, etc. up to xn, some n finite values are given. Correspondingly, y naught, y1, etc. up to yn finite values are given. So we compute first forward difference, second forward difference, etc. So delta y naught, delta y1, delta y2, etc. up to delta yn minus one we compute. Second forward difference, delta square. So initially, suppose that some five values are given, y values are given. So the first forward difference we are computing using y1 minus the formula y1 minus y0, y2 minus y1, y3 minus y2, etc. up to yn minus yn minus 1. Okay, and that's the first difference. So once you first forward difference, after computing the first forward difference, the same way difference is found of the first forward differences, and that's the second forward difference. So like that, we go up to whenever two terms are remaining at the end, that will be the final difference that we are computing. Whenever only one term is remaining, there is no more differences to find. Okay, that's what the technique is. So the forward difference, the forward differences we need to find first of all. Let us try Newton's forward difference interpolation first. Starting a new program, 40, 50. Newton's forward difference interpolation. So suppose that as in the previous case, let us construct x values as well as y values using some function so that we can easily create some. See, if you already have a list of values, then we can straight away use that. If you already have a list of x values as well as y values, we can straight away use that. But if you do not have any values, for understanding how the technique works, we need to create some x values as well as y values. So if a familiar function is there, you can make use of, then straight away use that. That's it. So x points as in the previous example. So importing numpy as np dot linear space, creating the points. Again, once again, 0 to 2 or 0 to maybe even 5. Say 20 points, y points. Let us try to create the same thing again. Y points equal to x points square. See, the good thing with numerical Python generated, linear space generated, or a range generated array, the good thing with that is you can straight away square. You can straight away apply functions like sine, but sine imported from NP. The usual sign from math cannot be applied. Sign imported from NP can be applied. Okay, so this is computed. Now we need to compute the differences. The first difference, second difference, third difference, etc. we need to compute. So compute the first differences. First forward diff. So how do we compute the first forward difference? The thing is that we need to take each and every point in y points. We need to start with y1 minus y0. Okay, y1 minus y0 we need to find. So there is a divided difference formula also. That's another thing. Y1 minus y0 we need to find. Y2 minus y1 we need to find. Let us create that. So instead of that, can we directly use diff? If you use diff, what will happen? Diff is also going to give y1 minus y0, y2 minus. Okay, diff is enough. NP diff. For finding forward difference, NP diff is enough. Diff by pt is. Let us see what it is. Forward difference, or otherwise f diff 1. So let us see y points first. To make things easier, let us try to put only 10 points. Okay, saving it. Save. Oh, only the differences are shown. Let us see the y values also. So the y values are here 0, 0.3. So the first difference is 0.3 itself because we are starting with 0. Next is 1.23. 1.23 minus 0.3 is around 0.9. That's perfect. That's correct. So first differences are out here. See, the good thing with NP diff is that we don't have to do it in a loop. Otherwise, we may have to do it in a loop. Just 1 second. So we need to take the gap. So okay. So anyway, so this is the first difference, and how many differences we need to take here? So how do we determine how many differences we need to take? We need to take the difference as long as more than one terms. At least two terms are differing. At least two terms are existing in the difference table. We will keep on finding the differences, but that we can actually automate. So forward differences equal to, let us put it as an array, forward differences. So initially we have this one. So what should we do? Initially we computed this forward differences equal to initially what should we do? Initially we can take, so we need y0 also. Therefore let us put the first one to be consisting of this. So let us append. Okay, let us append this. Remember that how do we compute the forward difference table? So we take y0, y1, y2, etc. up to yn. After that, we take y1 minus y0 y1 minus y0, y2 minus y1, etc. So, in the forward difference interpolation formula, what happens is that the topmost differences are important. That means delta y0 is required, delta y0 is required, delta square y0 is required, etc. These values are actually required, and other values are not at all relevant for us. Okay, so the topmost values are actually required, and for finding the topmost values, we need to we need to what you call keep track of only the topmost values. That's what the formula is, according to the formula. So forward differences we are appending YPTS. So as long as the last forward difference we found has more than one value, we will keep on continuing forward difference. That's a technique. As long as the last forward difference, keep in mind, as long as the last forward difference, that may be the zeroth forward difference, which is y points itself, first forward difference, which is y1 minus y0, y2 minus y1, etc. As long as the forward differences, that list, the last one, latest one appended to that consists of more than 2 points, we keep on continuing the forward difference. Okay, that's what essentially the technique is. So we have appended. So while, so how do we take the last one? Remember that now, okay, just 1 second. Keep it as an empty list, first of all. While, uh, what do we need to do? Take the last element in this forward differences, last item. So this is the list. This is the list consisting of, again, arrays. So the only one element in this list as of now. Okay, I'll try to show that first. So this is a list. Inside that there is an array. Okay. So let us take that array and find the length of that. So take which array? The last array. How do you find the last array? Last array is length minus 1. While, okay, let me copy paste. Last one. That's a dynamic thing because every time we are appending it. Length of this minus 1. So the last one has more than one element. Length is greater than. What should we do? Take the last one. Take the last one. And which is the last one? So that's only here. This is the last one. I think one bracket is not appearing properly here. Length is matching. Square bracket length is matching. Okay, it should be here. Okay, let us try to see the result of this. Print. Let us try to put 4 points inside that. First of all, not so 0 to 2. Just take 4 points. How many are there? So this is array number 1. These are the values 0 to 4. The interval 0 to 4 is divided into 4 pieces. So 0, how is it divided? 0 to 4. 0 to 2, sorry. 0 to 2, how is it divided into 4? So 0.5 it should have been, but why is it dividing it into 0, 0.4, 1.7 and 4? Why is it like that? What is being printed? Okay, this is y points, sorry. So these are the initial values, 4 values are there. After that 0.4, 1.7 minus this, so how many are there? 1, 2, 3 values. After that 2 values, after that only 1 value. So forward differences are all computed. I am updating the Google document, you may try. Let me try the Google document. Done. Please try. Now we need the formula. Okay, once we have, okay, is there any, no, there is no spacing issue, it's perfect. Now, what is the next thing that we require? That we require is the formula for finding the four-way difference. The formula is that, so we need to take a difference. So, Newton's four-way difference formula actually assumes that you are spacing the points at equal distance. Okay, so we need to find out the difference between the points, and difference between the first 2 points. You can see that. Okay, we need to find something called h. Now, equally spaced points. Anyway, we have taken equally spaced points. So, h equal to. So let us take the first 2 points and find the difference of that. X points 1 minus x points 0, assuming that at least 2 points are definitely there. What is it? Why is it giving? Okay. So after evaluating this h, we need to evaluate something called, we usually evaluate something called a polynomial p. P is nothing but p is taken to be equal to x minus x naught by h. So x is required. So let us take from simpy import symbol and create the variable x or symbol x. Now p equal to, it's a part of the formula, p is equal to x minus x pts 0 uh, divided by h. Okay. Now the formula is that the forward difference interpolation formula is that Newton's forward pole. So we need to compute y naught plus p delta y naught plus p into p minus 1 by 2 factorial delta square y naught plus p into p minus 1 into p minus 2 by 3 factorial delta square y naught plus etc. So this p into p minus 1, okay, these things we need to just see. We need to remember that all the forward differences we are using, and we have forward difference up to what? Here we have y naught is there, delta y naught is here, delta square y naught is here, delta cube y naught is here. So we need to go up to delta cube y naught. So how many arrays are here? 1, 2, 3, 4. So we need to go up to, so 3 arrays are here, therefore we need to go up to the third difference. Okay, that's what we want essentially. So up to the third difference we need to go. So we need to keep on adding something. So the formula is that, I will write the formula first. The formula is that P, sorry, not P, y of x is equal to y naught plus, I'm just writing y naught here, y naught plus P delta, delta y naught is the first forward difference, delta y naught plus P into P minus 1 by 2 factorial, 2 factorial. Delta square y naught plus etc. Go on like this. Okay, the function factorial must be already there in NumPy itself, but the only thing is that p into p minus 1, p minus 2, p minus 3, etc. Okay, p itself consists of symbol, and I think we need to be really a bit careful. So we may have to probably compute it ourselves. So this factorial function is it's okay, but sending this symbol to the factorial function can be a little bit difficult. So to avoid that, let us do it manually. So from where to where we have to go, we need to compute p into p minus 1, p into p minus 1. So the pieces initially we compute. Okay, the pieces initially compute. Newton's Pauli parts. Initially we compute the parts. After that, we sum all of them. 4, from where to where we have to do. So up to how many differences we have? We have up to the third difference, that's separated from array here, array here, array here, array here. We have up to the third difference, so we need to go up to the third difference. So we need to make use of all these things, and we need to take the first element from each and every array. So we need to find how many differences. Differences count. Difference count is equal to length of forward differences. This is the count we have. So for I in range, so p to p minus 1, p minus 2. Okay, I in range. So we need to find up to how many differences we need to find. Okay, let us take it to be difference count. Plus 1 is probably required, because we need to count up to, let us take it anyway. What should we do? P into p minus 1 into p minus 2. So initially we need to take just p alone. The first one is not even p. The first one is actually yeah. The formula is y naught plus p delta y naught. Okay, y naught plus p delta y naught plus p minus 1 by 2 factorial delta square y naught plus. So this delta y naught etc. All these things are there with us. The only thing is that we require y naught is also there. That is also in the differences, forward differences connection. The only thing is that we require p into p minus 1 by 2 factorial we require, p into p minus 1 into p minus 2 by 3 factorial we require. Maybe that is essentially This is nothing but if you remember about the combinatorics, the combinations, that is nothing but NCR or NP, NPR. So NP or NPR essentially means that n into n minus 1 into n minus 2 into etc. up to n minus r divided by 1, 2, 3, etc. n minus r minus 1 etc. up to etc. divided by 1, 2, 3, etc. up to r. Okay, that's what NPR is. Essentially the same thing we are doing here also. But problem here the problem here is that we don't have a number at the place of p. The place of p we have p is nothing but x minus x naught by h. That's in a variable. So that's in a variable. Therefore, we need to multiply. Okay, we need to multiply this variable name. So p into p minus 1 into p minus 2 by 3 factorial. We need to multiply. So how do we do that is the only question. So what is the first thing that we need to multiply? Okay, I'm calling that as p part. So initially it is just equal to 1. So after that we will multiply with the forward difference. So p part is 1. What next? So depending on what, this is the formula that we have to, I will just type that once again. So this is the formula that we have to evaluate. How I typed it anywhere here? No. Yeah, it's already here. So p into p minus 1 by 2 factorial plus p into p minus 1 into p minus 2 by 3 factorial. So this is into d y naught. So this is the formula that we have to evaluate, and the most important thing that we have to compute is p into p minus 1 by 2 factorial, p into p minus 1 into p minus 2 by 3 factorial. This is the most important thing that we need to compute, because afterwards we can simply multiply y naught into 1, because we are taking the first part to be equal to 1, y naught into 1, delta y naught into p, delta square y naught into p minus 1 by 2 factorial. These things can be multiplied easily. But how do we find this p into p minus 1 by 2 factorial, etc.? That's what I'm thinking. How do we find this p into p minus 1 by 2 factorial, etc.? For finding p into p minus 1 by 2 factorial, etc. So p need to take p minus 1, we need to take, okay, p combinatorics, we just put it like this, or PCR we call it. So PCR, computing that itself is a little bit difficult. So PCR, how do I compute PCR here? So p into p minus 1 okay, let me just try one method. So p into, so initially it is just 1. So initially it is just 1. After that, okay, let me append this to Newton's body parts. Let me start here. After that, what should I do? So p by 1 factorial I should multiply. After that, p minus 1 by 2 factorial I should multiply. After that, p minus 3 by 3 factorial I should multiply with the previous thing. Okay, I think that should work. So this is already here. Now next is that multiply with the last one. P part equal to multiply with the last one. Last one means length of this. This is the last one. So already we have one there. With this, what should be multiplied? P by which factorial to be multiplied. So if the length is 1, then 1 factorial should be multiplied. Okay. I'm sorry if it's a complicated method. I don't see any other easier method here. So this factorial is required, right? 1 factorial, 2 factorial, etc. So from numerical Python, import factorial also. Not necessarily. NP we can use. NP dot NP dot factorial is not there. Oh, there is no factorial. Maybe I should import math. Math dot. Math dot factorial. So let me see if the logic is correct. So what I'm trying to do is, so initially, see, I need to construct this. Okay, I need to construct this finally. This is what my aim is, constructing this polynomial. So what I'm trying to do is, I'm constructing another list in which the first element is 1, second element is p, third element is p into p minus 1 by 2 factorial, or p into p minus 1 by, second element is nothing but p by 1 factorial, third element is p into p minus 1 by 1 into 2, 1 factorial into 2 factorial, which is essentially p minus 1 by 2 factorial into the previous thing. And the fourth element is p into p minus 1, p minus 2 by, oh, this is not correct. Okay, this is correct. So this is 3 factorial. 3 factorial is essentially multiplying. Okay, then in that case here, multiplying with this is not required. Only 3 is enough. Okay. Okay. So what I'm trying to do is, initially I have taken p part to be 1. Okay. See that. Initially I have taken p part to be 1. I will multiply that with y naught. Secondly, next p part is taken to be, so the previous p part, which is Newton's polynomial parts, length of Newton's polynomial parts is at present 1. So minus 1 means that it is a 0th element, which is already 1. So with that, we are multiplying p by 1. Okay. After that, what will happen is, it already consists of p by 1. Multiply that with, okay, not p by 1, p minus 1 and p minus 2 I should take. So p minus 1, how do I get that? Here again, once again, I should multiply with, okay. So this length of this p parts, remember that length of this Newton's poly parts is increasing in every step because I'm keeping on appending. Okay, I'm keeping on appending. Okay, let me just see if I have done it correctly or not. I'm just experimenting with all these things. I'm trying to print. Is this complete? I completed this. Newton's poly parts. The previous part with which I am multiplying. This is taken. Length is taken. Yeah, I think that's correct. Now, trying to print this thing to see if I have done it correctly or not. Y is not defined. Where is Y? Ah, here. Sorry. Built in, it's not subscriptable. Which is not subscriptable? P minus length of Newton poly part. Length of Newton's poly parts Oh, length is in ordinary bracket. Sorry. Here also length is in ordinary bracket. Length is in ordinary bracket. Length, length. P is not defined. Where is this P? Haven't I defined P anywhere? Okay, I have not defined P. Okay, P is equal to x minus x is defined here. So P is equal to x minus the zeroth x point divided by h. So this is what's happening. So what is P? Let us see. P is 1.5x. So 1.5x, 1.5x, what is being P? Next is, okay, what's happening? First is P. What is the next thing required? So P minus P into P minus 1. So this is P minus 1. Next is P minus 2. Okay, P minus 2, P minus 1 by 2. Okay, that's fine. P minus 3, P minus 2, P minus 1 by 6. Okay, seems to be somewhat okay. So the parts are there. Now the summation. The summation is here. So for summing, what we need is the polynomial. The polynomial is here. So for that, I need to take all the y values. Where are the y values? Have you already completed? Yeah, it's here. All the y values we need to take. So list comprehension probably we can use, and the sum also. Sum of what? So sum of y naught into 1, p into d y naught, etc. we need to take. So how do we use that? Y naught, y1, etc. are appearing in where these things are appearing. These things are appearing in the four-way differences. So we have kept everything in the four-way differences. So four-way differences, inside that there are several arrays. So each array consists of the first four-way difference consists of y0, y1, y2, etc. Not the first four-way difference. The first element in the four-way difference, that itself is a list consisting of y0, y1, etc. First element in the four-way difference is taken to be four-way difference 0. Okay. Inside that, the first element, that is four-way difference 0, 0. Remember that there are two subscripts. Those second element in the four-way difference is second four-way difference, which is four-way difference 1. From that, we need to take the first element. Therefore, four-way difference 1, 0. And after that, four-way difference 3, 0. Okay, this is how we have to take. Now, sum forward differences. So, shall we keep I 0? So 1, 0, 2, 0, 3, 0 like that. Star. Multiply with what? Newton's poly. Parts I for I in range. So how many? Length of four-way differences is fine. Differences count. Differences count is enough. So we have taken 4 points. Print So the polynomial finally is this. Maybe we can expand also. This is a degree 3 polynomial. As in the previous case, let us try to plot it and see it in action. So seeing it in action, PLT, plot. The x points and y points are already here. X points, y points. Okay, we have taken x square. So we have taken only 4 points. Maybe we can take 10 and PLT show. Okay, it appears to be this. Maybe we can take on either side of, so that and take 20 points. So it's here. Now try to see the polynomial also. How do we find the polynomial? We need to evaluate, right? I think Lagrange's interpolation I have already updated in the Google Sheet. Okay, let me see. Lagrange interpolation is always it's all Newton's four-way difference. See, it's already updated except this one. Everything is updated, and the link is also shared. Do you want me to copy paste the link once again? The link is here once. Except these things, I have updated. Okay, this also I will update. This is okay. So okay, now we need to find y points also corresponding to this Newton's polynomial. So how do we find? Yeah, Akshara, is there any question?
Sorry, sir.
Okay. So we need to evaluate this y points correspondingly. For evaluating y points correspondingly, maybe we can do it here itself. This is a symbolic Python related variable is there. Therefore, we cannot straight away use that. It's not possible. So we need to evaluate it one by one. That's the problem when we are mixing up symbolic Python and Newton. It's numerical Python. So what is it we have to do? Newton's poly substitute for x value for x value in x ETS. So two plots. This is done. Plotting is done. This is done. This is done. Let us change the color to red, diamond to C. If it's appearing properly, prime. Seems to be somewhat okay. Not perfect. Seems to be somewhat okay. Maybe we can try with sine pi itself. Okay, somewhat reasonable. Not perfect, it's reasonable. Okay, let me update the entire thing in Google Sheet once so that you can have a look at that. Update. So backward difference also can be done like this. See, the only thing is that once you are able to do some one problem, most probably provided that you understand the technique correctly, you will be able to code anything. The only thing is that you need to get a little bit more experience in writing the code. That's it. Otherwise, there is not much. So this forward difference, backward difference, all these things are used when you have the points equally spaced. The points are equally spaced. Okay, when you don't have the points equally spaced, you need to use uh, divided difference formula. So instead of using the difference, because the difference when we are taking difference formula is applicable provided that the differences are uniform. The divided difference, what's happening is that we are dividing with the x value differences. Okay, let me just copy paste the feedback link. Okay, so if you want to see the divided differences also, the only major difference here is that when we try to find the difference, so when we try to compute the forward difference, so backward difference there is no difference. The only thing is that you need to compute the difference from the in the opposite direction, right? We just try to see at least the difference we can try to find out. Afterwards, the formula is exactly the same. I'll try to show at least that in the case of forward difference, we are finding y1 minus y0 and so on like that. But in the case of backward difference, what do we do is uh, y1 minus y0, y2 minus y1, etc. are actually found. And after that, we are finding delta yr minus yr minus 1, but instead of delta y naught appearing on the top, we will be having the last difference surviving till the end. Okay, that's the difference. I think Probably the only thing left is, okay, curve fitting also I will try to show once how to do the curve fitting exercise. So instead of doing all these things, instead of constructing all these things, we have constructed Newton's polynomial, we have constructed Newton's forward difference polynomial, Lagrange interpolation polynomial. Actually, numerical Python offers a function called interpolation itself. The function, the interpolation, the thing is that you are not actually going to get a function or anything like that, but instead of that, you will be getting the newly interpolated value straight away. Okay, the newly interpolated value you are going to get straight away, and there is actually for finding the interpolation polynomial itself inside Python. There is actually an interpolate function available. I'll just try to describe these two and stop with that because we can continue with the curve fitting and all these kinds of things. Not tomorrow, but day after tomorrow. Tomorrow we will not be having any session. Tomorrow 17th we don't have any session, but 18th we will be continuing with all these things. But before that, I would like to just introduce the interpolation function itself. Okay, so given x and y values, we can straight away find corresponding to this set of points, corresponding to this set of values, how to locate a value. Okay, let us just try to see. So here, I'm starting a new. So straight away I'm finding, without using this Newton's polynomial or Lagrange polynomial, straight away finding the interpolation value. So the program number is 51. Interpolate NP. So in this, suppose that we are using x is equal to once again x points. So let us use the same convention. X points we are creating. Numerical Python importing. Import numpy np. So x points are np dot linear space 1 to say 0 to 2 once again. So take 20 points. Y points are correspondingly, let me take x points squared. Now suppose that, so what are the points given here? Suppose that, let me find out the value corresponding to 2.1. Okay, so x outside equal to 2.1. So finding the value of x outside, which is 2.1, using the x points and y values, what we should do is we need to just take the interp function. Okay, y outside equal to np dot interp, interpolate. So x value, give the x value, give the x points, give the y points. Let us see the y value. The y value is this, and let us see the actual value. The actual value is x value square because we have taken the square of the function. We need to save it. Saving. The actual value is 4.41, but here it's given to be 4.0, not a very good estimate. Let us try to increment. Why is it happening like this? X outside is taken to be 2.1. Y outside is, okay, this is the approximation is not very good probably. Maybe if I take something in between, then 1.75. Okay, the interpolation is inside probably. So inside it's giving somewhat better approximation because the value given here is 3.0625 and the actual value is 3.625. Okay, let me just update the Google Sheet with this, and probably I will stop with this. So the Google Sheet is updated. As I told, tomorrow we don't have a session at 6 o'clock, but day after tomorrow on 18th onwards, we will be having sessions. And on Saturday, I think as previously announced, we will be having Saturdays and Sundays, um, 10 o'clock in the morning. And since we are dropping one session, tomorrow session, we will be having sessions on 21st as well as 22nd. We were supposed to finish on 21st, but we will be finishing only on 22nd. So thank you very much for your patient listening. If there is any clarification required, I can try to give. Thank you once again.
Thank you, Vishnu sir, for this information because today's class is finding for using Python programming and actually finding forward differences using a scientific computer, it is very difficult and time consuming. But using Python program, I think it is very easy. Thank you, sir, for this information.
Yeah, the thing is that you should. The problem is that if you are using C programming or anything like that, you don't have actually a function like npdiff.
Oh.
npdiff is quite useful. It's an excellent function, and straight away you can keep on finding, and all the forward differences are collected into one particular array. That's it. That's the most interesting thing. And the thing is that I find out all these functions when I actually go for some lecture, because otherwise I am not using these things. Numerical Python, numerical analysis related things. Those things are not really useful for me because my area is not exactly like that. But whenever I have to give some lecture, then only I start exploring that how to do this problem. And
that means C program is better.
No. What I'm saying is C programming. You don't have a function like this. npdiff diff function is not there. You have to do it manually. It's really difficult. It's really difficult. Python is much more simpler in that way.
So it is very informative today's class. Thank you, sir.
Thank you very much, ma'am.
Thank you all. Okay, good night.